Hello everyone, my name is Aniat and today I'll be covering the problem number 2, implement Dijkstra's. In this question, we need to implement the Dijkstra's algorithm, which given a node S, outputs the shortest distance from S to every other node. We're also said that G here is an edge adjacency list, where every index represents the list of tuples. The first element of each tuple represents the other vertex that edge is connected to, and the second element represents the weight of said edge. We're going to delve into this very soon. Now, let's look at the helper functions that were given. If you noticed, all of them are for min heaps, which is a big hint because we're going to use min heap to implement the Dijkstra's algorithm. If you look at the signature of this algorithm, the first argument is going to be G, where G is the edge adjacency list. So what is an edge adjacency list? Imagine that we're given the graph on the right side of the screen. Here, 1 is connected to 2 by an edge that has the weight 1. And of course, 2 is connected to 3, 4, and 1 with edge weights 3, 2, and 1. If you want to represent this graph in a very efficient manner, you're going to use an edge adjacency list representation. And it works in a very simple manner too. For example, first, notice that the node 0 is connected to the node 4 with an edge weight 1. And here, the index 0 has an list that has one tuple inside of it. Why only one? Because there is only one outgoing edge from the node 0. And the first value in the tuple is 4 because 0 is connected to 4, and the second value is 1. And here it gets a bit confusing. So where did we get the value 1 from? Essentially, 1 here is the same as 1 here, and both of them are used for representing the weight of this edge. Now let's look to a bit harder example. So the node 2 is connected to 1, 3, and 4. So how will we represent that? First, the node 1 is connected with an edge weight 1 to our node 2. And next node is going to be 3, which is connected with the edge weight 3. And lastly, we have 4, which is connected to 2 with an edge weight of 2. If you also noticed, here I'm representing the adjacency list in an increasing order. So the first node is going to be 1, the second node is going to be 3, and the last node is going to be 4. This is just a convention that we use to show the edge adjacency list representation. Now, let's think for a second. What does this function, Dijkstra's, returns? So it is going to essentially return two things. The first one is going to be an array, which we'll call distance. And of course, you can guess that it's going to return the distance to every other node. And the second one is going to be equal to breadth. And what is breadth? So imagine that you have found that the shortest distance from, for example, 1 to 4 is going to be from 1 to 2 and from 2 to 4. However, even if you know the value in the distance array, you don't know how to get to the value 4. Yes, like, do you go from 1 to 2 and from 2 to 3 and from 3 to 4? Or you just go straight from 1 to 2 and from 2 to 4? To determine this, we're going to use an array called breadth, which works in a very interesting manner. So let's say that we want to show that the shortest path to the node 4 from the starting node 1 is through the node 2 and from the node 2 to the node 4. So we're going to create an array pref, which will have 1, 2, 3, 4, 5 values. So let's make a very large array. And we're going to essentially fill it with -1s at the start because we don't know what path we need to take to get to the node 4. And apart from that, we're going to put indices on the top, just so it'll be easier to see. So from the node 1, we need to travel to the node 2. So we're going to say that the pref of the node 2 is going to be equal to 1. We're also going to change the pref of the node 4 to 2. And here, you notice that if you follow like the pref values, so like to get to the node 4, you need to go to the 2, and from 2, you need to go to 1. And now you determine the path to the node 4. So just by using the array previous, you can find a path to every node from the starting node. So I hope that my explanation wasn't too hard, but now we need to ask ourselves, what is the length of those two arrays, distance and previous? So previous needs to have 5 values in the example that we covered previously. And 5 is the number of nodes that we have in our graph. And the same goes for distance. So how many values can we have in the distance array? So intuitionally, we know that we need to find the shortest distance to every node in our graph, which means that we need to have 5 values. Therefore, we're going to create an integer, which we'll call n, which is going to be equal to g.length. And of course, in the example on the right, g.length returns 5. And now we can create two arrays. The first one is called distance, of course. It's going to be an array that has n values. All of them are equal to 0 at the start, of course. And the second integer array is called previous. It's also going to have n values. Now we're going to spend this whole for loop to fill out those two arrays, distance and previous. The distance array needs to be filled with plus infinities. Why? Because at the start, we don't know the distance to any node. So we're just going to say that distance v is equal to integer max value. Now we need to set previous v to -1, 2, just like we did on the example above. Lastly, we're going to spend this line to say that the distance to the node S, which is our starting node, is equal to 0. Why? Because to travel, let's say, from the node 1 to itself, we're not going to spend any moves. And this line is going to be spent on creating a min heap. So we're going to say that our heap is equal to min heap, heapify distance. So why did we heapify the array distance? Because we are going to pop the shortest edge that we haven't covered yet. So starting from the node 1, we are essentially aiming for finding the shortest path to the node that is connected to it. In this example, it's going to be 2. So we're going to use our while loop to pop the values from the heap and also check if the heap length isn't less than 0. Let's say that u is equal to the top elements of our min heap. We're going to call heap remove min to denote that. So now we're going to use edge index. Actually, let me write it in a bit shorter way. So edge index. Edge index is at the start equal to 0, and it can climb up until it reaches GU, that length. And of course, edge index is going to be incremented by 1 every time. Now we're going to essentially check if, for example, if we are considering the node 0, we're going to check if the distance to it hasn't already been covered. And if it has been covered, we don't need to change the distance to it. If the one that we've found currently, it's longer than that. And we're going to check it by saying that V is equal to GU edge index 0. And of course, on the example above, we can denote like for if our u is equal to 0, v here is going to be equal to 4. So now we need to check if the distance from 0 to 4 hasn't already been found. So if distance v is more than distance u plus gu edge index 1, we can update the distance to v with this value. So let me copy it and put it here. Lastly, we need to change previous array and say that the previous v is now equal to u. And of course, do not forget to change the key of the value v to distance v. Why? Because in our heap, every element is ordered by their key. And since we've updated the distance and our heap, if you remember, was also made using the distance array, we need to change the key of the value v to the new distance. At the end, we're going to return ref. This is all for this problem. Thank you for covering it with me.